Morning, everyone. So yesterday we took a look at buffer solutions. The goal of a buffer is to be able to maintain the pH, not let the pH change really wildly, either going too basic or too acidic within a small addition of acid or base. We found that for a buffer system to work, we relied on something to be either weak acid or weak base. Those would come with an equilibrium that can definitely shift to respond and get rid of any excess H plus or OH minus that we toss in. We also needed to beef up the conjugate form, so that way I can actually shift in both manners. So I'm just going to give you a quick practice question on buffers, just to clarify a little bit, after which we're going to take a quick look at oxides and then a few other side notes. So just for practice here, I want you to identify in this first question here which of these mixtures I'm going to be hinting at. Which mixtures can form buffer solutions? So I'm going to give you, let's try HCl and NaCl. We'll do our Chiku, and I'm going to add in potassium acetate. Let's try ammonia, and let's add in LiF, and let's do HF and NaOH. Okay, so that's the first question here. Second, I'm going to give you an example of a buffer system, and I just want you to just describe it a little bit here. Explain what happens to the buffer system when H3O plus is added. And I'm going to give you, this was a hydrogen phosphate buffer, so this is something that we naturally have working in our body, so it can help maintain the blood's pH. So H2PO4 2 minus with water in equilibrium with HPO4, sorry, this is -1, and this one is H3O plus. Okay, so I'd encourage you just to pause the video, try it out for yourself, and then when you come back, you can check your work with me. For this first one, again, for a buffer, it's pretty basic question that they're going to ask you. You're going to be looking for having what it's called appreciable amounts. So you need to have good amounts of both conjugate forms. And we had already talked about here, we want things to be weak, so therefore you would have an equilibrium. So this first one here, you just ask yourself, what are these chemicals here? Well, HCl is a strong acid, so this one here would just go in one direction. This one here would not be able to end up in equilibrium, so therefore there would be no shifting involved. So this one here wouldn't work. This is our standard acetate buffer here. Acetic acid by itself is a weak acid, so we do have that equilibrium. Unfortunately, as a weak acid, its constant is very low. Reactants are heavily favored. There's only a really tiny portion that actually goes to the other side. And here we are adding a salt. Right? Well, where'd the potassium come from? Well, the potassium is just an alkali salt, so this will break up to become K plus and acetate. This will artificially beef up the conjugate amount. Yes, as you add in that conjugate here, it would already be shifting, but we can settle into this sort of equilibrium where we have good amounts of both. We'll see this in the latter question here. If you add H plus, I have enough acetate to shift over. If you add OH minus and pull down the H plus, I have enough acetate to shift over as well. So this one can be an it's actually an acid buffer. Buffers have to be able to buffer both additions of acid and base. The reason why I call it an acidic buffer is it buffers in the acidic region. What about this one here? I have NH3 and LiF. NH3 here is a weak base. If you look at the equation though, NH3, I'm going to write you the whole equation. This becomes NH4 plus and OH minus. Again, as a weak base, this one here does not ionize very well. So you're only going to get a tiny amount of ammonium, tiny amount of hydroxide. We need to beef up the amount of ammonium. Well, I am adding a salt here, but this salt here has nothing to do with my ammonium. It's not going to beef up my ammonium content, so therefore I can only shift one way, and therefore this is not a buffer system. This last one here is a sneaky one. They probably wouldn't ask it in this fashion, but let's just check it out here. We have HF. HF here is a weak acid, so that's potentially good. We have HF, it's in equilibrium with its F minus partner. Again, the whole problem with these weak things here, the Ka and Kb's are really tiny, so we're not actually getting a ton of the F minus or the H3O plus. Again, I am not actually adding a salt that actually contains a conjugate. So at first you're going to say, well, this is definitely not a buffer. But remember from last day, there was one other way we can make a buffer. In fact, what ends up happening, if I take a look at this HF equilibrium, because I'm adding a strong base, this is actually going to be put through a neutralization. So what's going to happen is HF is going to run into NaOH. It's the acid-base titration. The neutralization is actually one direction. So this is going to give you NaF and water. What I want to show you here is NaOH here being a strong base actually starts killing off the HF. We had put some numbers to this last day. Let's say I had 10 moles worth of HF. Well, then I would need 10 moles to cancel it out. What if we've only added a little bit of NaOH? I've added, let's say, 5 moles of NaOH. Those 5 moles of NaOH would start killing off the acid particles. I'd lose the 5 moles, I'd lose the 5 moles. Because I have not completely neutralized it over, I still have 5 moles worth of my conjugate acid form, and now some of it has been converted over to the conjugate base form. So in this system here, I've also been able to have appreciable amounts. Yes, it's not as high as it was to begin with, it's not 10, but I do have good amounts of both the conjugates, and that's all I need for a buffer system. So that's probably a really sneaky question. But a weak acid, if I neutralize sort of half of the acid, I can also get enough of the conjugates. Again, they probably wouldn't ask it in that fashion, but we did see that, so I just wanted to rehash that with you. Second one, looking in a little more detail. So we are told that this is a buffer system. No surprise, we are expecting this to be an equilibrium reaction. What they're doing is they're adding H3O+. Okay, so the stress is we add H+. Okay, so this guy here is going to go up. What does the Chatelet want to do? The Chatelet doesn't like the fact that this one here suddenly went up. The reverse reaction would increase. The equilibrium would end up actually shifting to the left. So equilibrium shifts towards reactants to consume the H+. Even though the ice table that we did last day, we sort of pretended, let's say I added 5 moles, let's say Le Chatelet completely gets rid of 5 moles. We learned from chapter 2, although it tends to counteract equilibrium, it never really brings it back down to what it was before. So if I just drew a graph of just plotting the H+ concentration, I don't really know what the starting number is, but upon adding it all of a sudden at T1, as it shifts to the left, this H+ is going to start dropping, but it's not going to drop back to what it began with. So all that to say, so the overall H+ would have increased. It would be higher than what it was before. The H+ has increased slightly by the time you reach equilibrium again, and therefore you can conclude the pH decreases slightly. So we are slightly more acidic, but it's not suddenly jumping down like we saw for some of those equivalence points on the titration curve. What would limit this buffer's effectiveness? Well, how the buffer is trying to moderate pH, in this case here, is try to shift left. I know I have a ton of H+, I just added it. What would limit it is actually this HPO4 minus 2. So in this system here, this would limit the buffer's effectiveness in shifting left. Because yes, I do want to shift left. Yes, I do want to get rid of some of the H+, but the second that I run out of this conjugate form, I can't shift left anymore. Any added H+ is just going to stick around, and the pH would just suddenly drop. Okay. So hopefully that clarifies a few things for buffers for you here. Today we'll end off with a really small section here on oxides. Sort of an application to this acid-base chapter. We're going to look at certain compounds. Oxides are chemicals that actually contain oxygen. Oxygen is usually the non-metal. It's something oxygen. And all they want you to do is just a sort of little memory aid here. There's different type of oxides that we have. First, we'll start off with metallic oxides or metal oxides. If the blank is actually made out of metal, so the left-hand side of the periodic table, metallic oxides experimentally, these ones here form basic solutions. Right. So let's take a metallic oxide. How might I get a metallic oxide to begin with here? Well, we can have Na2O, so sodium oxide here. What's going to happen here is because this is an ionic compound and it's also an alkali salt, this one here is going to break up 100%. It's going to produce 2Na plus and O minus 2. This sounds like a hydrolysis style question, which it sort of is. This guy here completely breaks up. Are there any spectators? Well, yep, sodium plus 1 is a group 1 ion. Group 1 ions are typically spectators. These are just going to swim around solution. The O minus 2 is not a conjugate of a strong acid, so this is not a spectator. And in fact, by the time you find this one on the periodic table, we didn't have a very long list of strong bases, but we have acids and bases here. We have the best bases sort of at the really bottom here. In fact, oxide minus 2, it actually is so good at gaining a proton, it's a one-way arrow and end up forming hydroxide. Again, that's been simplified. I want to show you what's actually happening here. The O minus 2 would look like this right now. It's stolen 2 electrons from sodium already. In the presence of water, however, what's going to happen? Let me just draw a water molecule. Oxygen here has so many electrons that it's actually going to donate a lone pair. One bond is made out of 2 electrons here. This is actually going to be called the coordinate bond or dative bond. This one here is going to create a new bond with the H, and these 2 electrons which used to hold the O and the H here will just jump over to the oxygen. So let's see what ends up happening here. The oxygen still has 3 lone pairs, didn't do anything. This one here has created a new bond to hydrogen. That bond would just look like a covalent bond after forming. Because as I pull that off, I'm just stealing the proton of it. It's going to be H+. I'm going to go up by a charge. What about the water leaving behind here? So water used to look like this because both electrons on its bond went back to oxygen as well. It also now has a negative charge. Now we've ended up producing hydroxides. So therefore, this is a basic solution. So pretty much any ability that you have, in this case here, O minus 2 reacting with water, any ability for us to actually produce oxide as a solution, they're a strong base. They're going to very quickly steal a proton and end up forming basic solutions. And pretty much all ionic compounds that have oxides will form this strong base and therefore basic. Right? In fact, even if you drop in the metal in solution, it already is basic. So people usually just memorize that. Metals tend to form basic solutions. What would then form acidic solutions here are actually our non-metal oxides. So non-metal oxides, right? These ones here are going to be covalent oxides. They're molecular compounds. These ones here certainly do form acidic solutions. And part of it is because they are molecular and they're covalent bonded, when you drop them in water, they do not actually break up. So let's start off with carbon dioxide. It starts off maybe gaseous, just in the atmosphere here. Upon touching water, it ends up doing a sort of really complicated synthesis reaction, and we end up getting carbonic acid. Notice that we are not breaking up. It's not a salt. It doesn't ionize. We don't get that O minus 2, so we don't get that strong base. So therefore, we've actually ended up forming something that ends up having an H. And this guy here, it's a weak acid. You'll find it on the table. This one here has the ability to release protons, so therefore, it's going to be acidic, diprotic acid. So because CO2 is naturally in our atmosphere anyways, the CO2 naturally makes our rainwater slightly acidic. And they've gone to measure this here. If it were just carbon dioxide in the atmosphere here, it would only be about a pH of about 5.6 or so, right? So slightly on the acidic side, but not by much. When we refer to acid rain actually refers to, we had our pH ruler here, 7 is our dividing line. Okay. Rainwater is already naturally acidic at 5.6 just due to carbon dioxide. We know that this is already acidic. When we talk about acidic rain here, usually we're talking about rainwater that's around pH 2 to pH 4 or so. So when we actually use the term here acid rain, it's because there were other non-metal oxides in the atmosphere. Those also produced extra acids in solution. When that rainwater rains down, it's definitely on the acidic side. So acid rain is actually a result of a lot of industrial products that we toss into the atmosphere, result of industrial products. And usually we say here, just for simplicity here, SOx and NOx. Okay, so some compounds that contain sulfur oxides, nitrous oxides here, this could be SO, this could be SO2, NO2, NO3. You'll notice all these ones here are non-metal oxides, so covalent oxides. They, like the carbon dioxide here, is going to synthesize, react with water to end up producing acids. And this one here would end up creating things like H2SO3, H2SO4, in solution. This one here would end up forming nitric acid. So in addition to carbon dioxide, which would naturally make rainwater already acidic, when we refer to acid rain, it's usually due to these industrial gases. You just want to recognize these SOx and NOx. They are non-metal oxides, so they end up producing acids in solution. So a really simple question they can ask you for this section here is just which of the following are acidic? So standard sort of multiple choice question here. They might give you Li2O, MgO, Al2O3, and SO2. Right. So this is definitely from the oxide section because they're giving you a bunch of these oxygen-style compounds. All you need to remember is, oh, a metallic oxide or an ionic oxide is basic. Well, this is a metal, and metal. I would imagine that those ones there would be basic. There's only one that's a non-metal oxide, so this is the choice here. This one makes a non-metal oxide. Or just doing some test-taking hints here. Well, if this is multiple choice, they can't all be right. Hey, 3 of them have sort of a metal in common. Probably it's the non-metal. They could also ask you this in another frame of mind here. They could ask you, actually I can clarify this here. Just based on this metal oxide, we had predicted that this one here were basic, but we're actually going to find maybe this is also a sort of a hydrolysis style question. Aluminum oxide here, remember aluminum was that it's going to end up forming Al plus 3, but Al plus 3 is actually this Al. It's complex with 6 waters plus 3 like that. And this one here was on the acid side of the table. This one here would actually be acidic as well. You don't need to memorize this. This one here is on your table. You can look back at the hydrolysis lesson to figure out this aluminum complex. But pretty much all we really care here is this one here is H+. So I threw in one to sort of cheat here. It looked like a metal oxide, but aluminum is sort of picking up some covalent character here. This one could be argued that it's actually acidic as well. But definitely the non-metal oxide would be more acidic. They may even say which of the following has a lower pH. So aluminum oxide is really weakly acidic here, whereas a non-metal oxide, it ends up forming things like sulfuric acid and sulfuric acid, so really, really acidic. Okay, so just a small side note there, metallic oxides are basic, non-metal oxides are acidic. Okay. I want to end off this lesson here with 2 other just practice problems. Okay. First one, I just going to steal from your workbook here. First question, I want you to calculate the pH of a saturated CaF2 solution, calcium fluoride solution, where they give me the KSP is 1.46 times 10 to the negative 10. Okay. So we're sort of stepping away from oxides now. We're just looking at generic acid-base problems here. We've done many questions by this point here in calculating pH. Remember, just because they ask you pH doesn't suddenly mean that this is acidic. They're just saying, where along the ruler am I? And they give you this compound here, calcium fluoride. They also throw in this term here, saturated. Well, we saw this in our previous unit. In a saturated solution, we basically have an equilibrium. We have undissolved material present. We have CaF2. It doesn't look like macroscopically anything's changing, but the dissolving is still happening. The calcium fluoride is jumping to become calcium and fluoride ions as these calcium and fluoride ions are matching together to recrystallize. So if we think back to Unit 3 here, we wanted to write out the solid on the left side, write out the dissociation, and also write out the KSP expression. Right. This was back in our solubility chapter. So just a nice recap there. Notice I'm not given any information, right? Remember, there are 2 ways of making the saturated solution. Either you had dissolved the solid and it follows a mole ratio, or you mixed in a solution with calcium and fluoride. Sure, you need to do dilution, things like that, but it doesn't follow mole ratio. Because I'm not told, let's just pretend I had actually dissolved the solid. Because that's going to be the easier way. That's going to say, let's dissolve an X amount of calcium fluoride. That would mean I have an X of calcium, 2X of fluoride, right? That's based on the mole ratio. Whenever you have at equilibrium the concentration amounts here, you can put these amounts directly into the KSP expression. The KSP here is essentially KEQ for this products over reactants. It's just that reactants were solid, so that one we can actually ignore. So let's try 1.46 times 10 to the negative 10 is equal to X times 2X all squared. I'll clean up the math a little bit here. 2X times itself is 4X squared times the X. It actually gives you 4X cubed. This first part here looks like a solubility style question. 1.46 e negative 10 divided by 4 with the cube root. This gives me 3.3 times 10 to the negative 4. Remember, even though you've done a lot of math here, go back and figure out what the question was asking. Well, they weren't actually asking me for X, they're asking me for pH. Well, how do I do this, right? Well, this one here was a salt. We had, in some sense, like the hydrolysis lesson, we've ionized it, we figured out the cation and the anion. Well, calcium is a group 2 salt, so this one here can swim around solution no problem. That's going to be a spectator. What about the F minus? In this chapter, we learned, wait, F minus is actually on the acid side of the table. It actually is a weak acid. On the table, right, we had acid and bases. We're going to see the F minus equation. F minus is actually base. F minus doesn't have any protons, but F minus on this side, it can pick up that proton and reform its conjugate HF. So being a weak base, if you know what the concentration is, you can start doing Kb calculations. Try that out for now. I had to do a little bit of work to actually calculate how much fluoride can actually dissolve in solution with the saturation. The fluoride is actually given as 2x. So what if I ask you this question here? Fluoride is actually given by 2x, so let's go 2 times this number here. I could have started this question right at the beginning. Well, if I had a solution that contains 6.6 times 10 to the negative 4 molar of the fluoride, would you be able to calculate for me the pH? At this point here, it ends up as a Kb calculation. So let's just do it completely here. Let's write out the whole equation so I can set up an ice table. We're going to get HF and then OH minus. Our ice table is before any picking up of protons. So F minus, sure, was a lot of work to actually get to this number. But this number here I get here is 6.6 times 10 to the negative 4. This is before any picking up of protons. So we're going to have 0 and 0 of the HF. As we start dissociating here, this is going to drop by x, this is going to gain by x, plus x like that. Anytime you have the I in the C row, you just do the math, 0 plus x, 0 plus x. This is 6.6 times 10 to the negative 4 minus x. And usually whenever you have the equilibrium row, we're ready to write the equilibrium constant expression, KEQ. But because this is a base, we're going to call it KB. KB is equal to HF times OH minus divided by the F minus content. Because this Kb is expected to be very tiny, we can make an assumption, although you need to write it down. Let's assume that 6.6 times 10 to the negative 4, it already was a tiny number, but let's imagine so tiny a fraction that actually goes over, pretty much most of it just sticks around. This is practically 6.6 times 10 to the negative 4. Okay. One other note here is, unfortunately on our tables, they actually don't give us Kb values. If I actually look on the table for this row here, they actually tell me the Ka value. The Ka value of HF is given as 3.5 times 10 to the negative 4. That's how good my partner is in actually coming forwards. If this is the Ka for my partner, how do I actually get the numerical value for Kb? The Kb for doing this reaction in reverse, remember, is Kw divided by Ka. So Kw is 1 times 10 to the negative 14 divided by this 3.5, my partner in coming forwards. So 1e negative 14 divide 3.5 e negative 4. This one gives us here 2.9 times 10 to the negative 11. And that number ends up going in for the Kb expression. So the Kb, like we just calculated, 2.9 times 10 to the negative 11. The HF and the hydroxide are given on the ice table. I put an x for them. So x times x. On the bottom, I was supposed to put this subtraction here, but because I made that assumption, now I just have 6.6 times 10 to the negative 4. I know we're dealing with really tiny numbers here, but you can actually solve for x. So let's take this Kb. I have the number unrounded, 2.86 times 10 to the negative 11, multiply 6.6 e negative 4. I'm going to lose a little bit on rounding there with the square root. X is now given as 1.37 times 10 to the negative 7. We've already done a lot of work to actually find all these unknowns. Go back and reread, what was this x actually calculating? Well, the x was actually the amount of hydroxide at equilibrium. What they want to know is they want to know the pH. So what you can do here, if this one here is now the hydroxide concentration, once this weak base here has stolen from water, it actually generates a little bit more hydroxide, usually neutral water, which is at 10 to the negative 7. We have a few more hydroxide particles. Let's find the pOH by taking the negative log of this number, 1.37 times 10 to the negative 7. negative log of this answer here gives us a POH of 6.862. Remember, the significant digits are after the decimal place. And finally, if I want to find out where I am on the pH ruler, assuming we're at 25 degrees, 14 minus this answer, 6.862, ends up giving you here 14 minus that. So pH of 7.138. Do a mental check for yourself. Does that mean basic? Sure, right? Anything above 7. It's just slightly above that neutral mark. So that question there, practice with you a little bit of solubility. Remember, you unfortunately can't forget about the previous chapters, but that's how it sort of links into this chapter here. I want to do with you one other style of question. This one could have been done back when we did our mixture section, but there's a slight little spin-off, and we'll end off with this question here. So another example here. They're asking in this question, what mass of HCl is needed to change 40 milliliters of 0.180 molar NaOH to a pH of 12.500. Okay, so it is a sort of mixing style question here. As always, I like starting off with a picture. We have sitting in front of me a 40 ml solution. Right? That's how much liquid is there. Currently, the concentration is 0.180 molar, and this is sodium hydroxide. This one here is a strong base. We'd expect the pH to be something bigger than 7. And in fact, being a strong base here, we can actually check what the pH is right now. So NaOH here is a strong base. That means my hydroxide concentration, the OH minus is 1-to-1 ratio. The OH minus is actually 0.180. We can do what we just practiced there. Let's find the starting pH. So POH is the negative log of this one. Hopefully you've gotten a lot of practice going around that box diagram so you know how to do this conversion. Negative log of 0.18. My POH is actually 0.745. Again, significant digits after the decimal place. So what's my pH right now? My pH is 14 minus this answer, 0.745. 14 minus this answer gives you a pH of 13.255. Okay? So if you stick a pH meter right now, it's reading 13.255. So it sort of makes sense here. We're going to then toss in a strong acid. The acid is going to generate some H plus for you here. We want to know in this question, kind of weird, we actually want grams of HCl, but so be it. We want to calculate how many grams of HCl do I add to this. I'm adding an acid to a basic solution here. I would expect the pH to gradually drop. And I want to add enough of it so that at the end of the day, my final beaker is going to be just slightly more acidic. I want my pH probe to now read 12.500. Okay? We can make some comparisons. So we know the pH at the beginning. I want to add enough H plus, kill off some of the hydroxide, and end up getting my pH final to actually 12.500. Right? So you can think in terms of acid here, how much does the H plus need to drop by? We're actually going to find it's much better looking at how much hydroxide there is. I'll show you both ways here. So we know the pH. While I have it here, let's find the H plus content in both situations. So the H plus is going to be the anti-log of negative pH. So let's go anti-log of negative 12.5. This gives me that the H plus content is some 3.2 times 10 to the negative 13. Really, really tiny number. At first, the H plus here was also a very tiny number. So anti-log of negative pH. So 13.255. Sorry, I should keep one more sig fig here, 3.16. The other side is anti-log of negative 13.255. This gives me here 5.56 times 10 to the negative 4. So the first way of just thinking about it, although this one here won't actually help me, we start off with this amount of H plus in solution, right? It's like a 10 to the this is 10 to the negative 14. So starting off here, not as acidic, right, because we're more of a basic solution here. I want to know how much H plus do I need to add until my H plus content is this, right? Now, first problem with understanding it this way here is this is a very, very tiny number. Wouldn't it just be a really small addition, like you need to add in 0.000, like really a tiny amount of H plus, and already we would end up hitting H plus? The problem you run into in that situation is, remember in the background we always have water, and water always has the ability to self-ionize. So water, as you start changing the solution here, water is always going to adjust, and it's always going to change H+. It's not so easy to just track such tiny numbers in solution. It's better yet, when we have hydroxide, that's actually a much larger number. Let's figure out how much of this hydroxide do I need to neutralize to end up giving you this pH 12.5. So let's just undo our work here. So pH is equal to 12.5. What is the corresponding pOH? 14 minus 12.5. So I want a pOH of 1.5. And therefore, the hydroxide still has to be fairly high. I need to go the anti-log of negative 1.500. Anti-log of negative 1.5 gives me here 0.0316. Okay. So again, there's two ways of thinking about this. One is you can think about, well, how much acid am I adding so that I can convert this starting amount of H plus over to this one, but those are all really tiny numbers, water sort of interferes. Or we can do it more, well, there right now is a lot of hydroxide in solution, that's why my pH is so high, it's 13.255. How much of the hydroxide do I want to kill off so that the pH of the final solution is actually 12.5? It's actually easier to do it with hydroxide because the numbers are a lot bigger and water wouldn't interfere. So let's just track the change here. If the hydroxide was 0.18 and I want to get it down to 0.0316, I'm going to just do a subtraction here. 0.18 minus 0.0316, I need to lose 0.1484 molar hydroxide. Okay. Well, what's helping to get rid of the hydroxide? Well, that's going to be HCl, and HCl reacts with NaOH in a 1-to-1 ratio. HCl neutralizes this, ends up forming NaCl, a neutral salt, and water. But being a 1-to-1 ratio, if you intend to kill off 0.1484 hydroxide, we actually then need to add 0.1484 H+. Right? And you notice that that is way more than I would have expected. Well, the H+ is only changing by a fraction, like 10 to the negative 13, something like that. And yet they're actually telling me now, no, I actually need to add in 0.14 molar H+. Water will then adjust and accommodate, and once your hydroxide has dropped to 0.0316, water will make sure of it that the H+ concentration is down to the 3.16. Okay? At that point there, we've basically solved through the problem. We're interested in finding the grams of HCl. We're going to take our volume, 0.0400 liters. The concentration of HCl I needed to add was 0.1484. That neutralizes enough base for me here. And then we just need the molar mass of HCl. So H is 1 plus 35.5 for chlorine. So that's going to be 36.5. And there we've done it. 0.04 times 0.1484 times 36.5. This one now gives me 0.217 grams of HCl. This is assuming that HCl is actually a solid. Usually it is a solution as well. But we've done it. I need to throw in the equivalent of 0.1484 molar H plus to kill off enough hydroxide for my pH to drop to 12.5. Okay? So keep practicing through your questions. Let me know if you have any problems. Thanks, guys.